Good morning, fellow mathematicians. Welcome back to another video. Today's video is going to be lit. You understand, because I'm flammable maths and we are making things burn on this channel. It's pretty nice weather out there today. So we want to derive a lot of classical mechanical stuff today from one simple formula. And the formula we are going to work with today is just some force dependent of x is equal to minus k times x. And you might know this formula. This is just Hooke's law. And you might be familiar with the fact that a force is nothing else than mass times acceleration. And this right here is a simple differential equation. And we are going to solve it today. And we are going to derive a lot of other stuff, for example, conservation of energy, or some little facts about potential energies for conservative forces. So let's go ahead and do this. So at first we are going to add k times x on both sides. So that's the first step. So 0 is now equal to m x double dot plus kx. And well, we are going to take for granted that the velocity can't be equal to 0. So we are going to multiply the velocity on both sides. It can be equal to 0, but we are going to assume that it isn't in this case. So now that means 0 is equal to m x dot dot plus k x dot times x. So that's great. But what can we do with that? If you've got a sharp eye, you might notice that we could factor out a little differential, a differential in terms of time. So we can rewrite this equation as follows. So this is just d dt times m over 2 x dot, but the whole thing squared, plus k over 2 x squared. And I hope you can see where this comes from. So if we distribute this differential into here, that means we have to use the product rule at first. So dragging this 2 down, that gives us m times x dot, but we also have to differentiate x, which is in terms of t, and that makes x dot dot. So we are going to get our original expression from this one right here. And one little fact, one crucial observation. If we differentiate something in physics in terms of time, and we are getting a 0 on the other side, that means that this term right here is going to be constant. But if you do some dimensional analysis, you might notice that's an energy and that's an energy. And the sum of two energies will also give us an energy. So this constant term right here is just the whole energy of our system. So that's the conservation of energy. That's nice. So that means that m over 2 x dot squared plus k over 2 x squared is equal to some energy, E. So that's the whole energy you put into your system. You might be familiar with those terms. This is just the kinetic energy, and this is some potential energy. So that's also T plus U is equal to E, where U is the potential energy and T is the kinetic energy. That's great. So we've derived something very crucial in physics, the conservation of energy. Let's move on. You might notice something else. What would happen if we differentiate this potential energy right here in terms of x, but a negative differential? Well, we would end up with our force. Let's write it here. So minus d dx of u in terms of x is nothing else than minus d dx k over 2 x squared. And what is that? Well, that's minus k times x, which was our original force, F in terms of x. And let me tell you something, my boys. This relation holds for all conservative forces. That's nice. And you could also say that the negative integral of F in terms of x is just u of x. It's kind of like the work done, but with a different sign. So that's great. So that's something we are going to use a lot later on. So that's the first part. And now what else can we take a look at? Well, since we are talking about potentials, why not take a look at the graph of this potential? We are dealing with a pretty simple graph in this case. So let's take a look. We have a graph right here. That's the x-axis. And this is u in terms of x. And you might notice this is just x squared. So it's proportional to x squared. And that gives us a parabola that goes through the point 0, 0 right here, through the orgo. Nice. And like I said before, we have some total energy. Let's put this total level of energy right here. So let's say that's our energy level E. Okay, but what does that mean? Let's take a look at it from a quality kind of way. Let's just imagine we would place some marble in here. And what would happen to a marble? Well, it would roll down and up again, and roll down and up again. So you can always use for those potentials this little analogon, like placing some kind of ball marble in there and it will roll up and down. And since we have no friction, it rolls from this point right here. We are going to call it x1 to this point right here, x2. And it will roll back and forth forever. And those are some crucial points. They are called the classical turning points. So we get some x1 and some x2. And those are the classical turning points. They are going to play a big role in quantum mechanics as well for some calculations. How can we actually define those classical turning points? So there's a way. So just imagine a pendulum, for example. It will swing up and down. And once it reaches this point, it does stop. This classical turning point, it does stop at this point and turns around. So the velocity is 0 at this point. So what does that mean? When the velocity is 0, well, our kinetic energy will also be 0. So for our classical turning points, if x dot is equal to 0, that does mean that our whole energy is just our potential energy. And it's at its maximum. So that's the highest potential energy you could possibly get. So that's nice. But we can actually solve for that, because this is just, in this case, k over 2, x max, but the whole thing squared. And now we can multiply both sides by 2 over k, take the square root, and what we end up with is just that our x max, 1 and 2, so plus minus x max whatsoever, is equal to plus minus the square root of 2e over k. That's nice. So we've defined our classical turning points. Is there anything else we can do with this graph? Yes, we can. Indeed, we can. So what would happen if... alles gut. So someone just came in, as always, when I'm filming here. Okay, so can we do the same thing for another situation? So let's just take a look at a situation where our marble rolls down and is at the point 0, 0. That means that our x is going to be 0, but our potential energy is dependent on 0. That means if we land in this spot right here, we are getting an expression for our maximal kinetic energy. So if x is equal to 0, that also means that our energy is just our whole kinetic energy, but the highest kinetic energy we can get. So this is m over 2 x max, x dot max squared. Okay, and now we can solve for x dot max. So that also means that x dot max is nothing else than 2 times e over m, but positive or negative square root. It does make sense that there are two solutions, because we can approach this graph from this side or this side. Either it's going to be a negative or a positive velocity, if you take a look at the vector. Okay, and that was a crucial observation. There's one other thing we can do. We can take a look at phase portraits. So what is a phase portrait? It's quite an important thing in theoretical physics. So a phase portrait shows you the relation of movement and position, for example. So let's put our movement here, velocity, and our position here. So we are having two highest points. So this is the first one and this is the negative case for our maximum velocity. But we also have two classical turning points. We have to place them on our graph. And I'm going to place it here and here. And now we can draw a graph like this. And notice I haven't drawn a circle that's more of an ellipse, because we are dealing with a parabola here. So it's not going to be a circle. And that's for our E, for our whole energy. And let's say, for example, we have a different energy level. That's like in here. We are going to call it E2. What would happen to our graph? Well, we would get a different velocity, and we are also going to get different turning points. They would be here and there in this case. So we would get a different phase portrait. So that's kind of important. So you are going to get a different phase portrait for different situations. We have done a lot of stuff. We've came pretty far. And now we want to solve this differential equation actually. We could solve for this one, but we want to solve for this one, because you might have never seen some kind of energy being solved. So let's do this. How can we even approach this problem? So like I said, we want to solve a differential equation. So we have to take a look at some time-dependent differentiated function. Well, we've got an x dot here. So we are going to isolate this at first, and then we can see what we get. So how can we isolate that? We are going to subtract our potential on both sides, and then we are going to multiply both sides by 2m, and then we are going to take the square root. So that means that x dot, which is nothing else than dx dt, and this is now plus minus the square root of 2 over m e minus k over 2 x squared. So that's the first observation. And we are only going to take a look at the positive branch. It doesn't really matter. So let's get rid of those signs. What can we do next? Maybe we could factor out a k over 2. So let's do that at first. So this is now equal to the square root of 2 over m, k over 2. This 2 and this 2 we cancel out. We're going to take a look at this later. Okay, next thing. So this is now 2 times e over k minus x squared. Whole thing in the square root. What is this expression? This does look a little bit familiar. Well, I've wrote it here. This expression right here is just x max but squared. So this is the square root of k over m x max squared minus x squared. Okay, nice. And now let's do some dimensional analysis. K over m, so that makes kilograms over seconds squared over kilograms, so those masses we cancel out, so that's 1 over seconds squared. Both are positive, so this is going to be positive and this is going to be positive. So we can break up this root and we get a square root of 1 over s squared. This is 1 over s. But this is just a frequency actually. So this is just, for example, our angular frequency omega. So this is omega times the square root of x squared max minus x squared. And that's nice. And now we are going to play physicist. And we are going to multiply both sides by dt. We are going to act like this is something that we can multiply or divide by. And then we are going to divide both sides by this term. So what do we get? Now we get dx over square root x max squared minus x squared is nothing else than omega dt. And now we want to integrate this because we want to solve our differential equation. So let's integrate both sides. And let's see what we get. We want to do this kind of cleverly. So what could we do? Maybe we can place some upper and lower bound and see what we get. So what could be our upper bound for here, for example? So we want to solve our differential equation. So we want to find an expression for x in terms of t. Okay, great. But if this is x in terms of t, then our time must be some point of time on this potential graph, for example. Okay, and we can take a look at one of infinitely many points of times or places where our ball can be. So let's just take a look at the highest point of the graph. So for example, let's take a look at the positive value of some x max. So that's getting a little bit tiny. So that's just the positive value of x max, for example. And we also have to take a look at the point of time at this point x max. So we are just going to call it t max. And solving this one right here is quite easy. It's easy to integrate, so that's omega t minus t max. And now we have to take a look at this right here. That's going to be quite easy too. What we can do at first is we could factor out an x max squared right here in the square root. So that's the first thing we can do. So we end up with the integral from positive x max to x in terms of t. And this is going to be 1 over square root x max squared, and then times 1 minus x over x max, but the whole thing squared. I'm going to put it that way. Okay, great. So that's a positive quantity, and this is also a positive quantity. So we can break this square root up and we get, I forgot the differential, so we get 1 over square root of x squared max. But that is just, well, that's the norm of x max. So 1 over the norm of x max. So this is going to be a positive value for x max. So let's see. We get 1 over x max, but the positive value at that. And then times the integral from positive value x max to x in terms of t of dx over square root 1 minus x over x max, whole thing squared. Okay, and now we are going to introduce EU substitution. So let's sum u equal to this term right here. That's why I put it that way. X over x max. Well, what do we end up with? Now we get du equals to dx over x max. But we know this term, that's dx over x max, which is going to be our new du. So now we get the integral. I'm going to put in the bounds later. Du over square root 1 minus u squared. And this right here is also a 1 squared. So keep this in mind. Okay, if we plug in x max into this x, well, we get 1 in this case. So this is just 1. And this is going to be x in terms of t over x max. Great thing. And what is this expression right here? I haven't derived this yet on this channel, but this is just the negative inverse cosine of u. So this is now the negative arcus cosine of u from 1 to x in terms of t over x max. If we plug a 1 into here, what do we end up with? Well, that will just be 0. So this is going to be 0. And if we plug this into here, it's just the expression itself. So we end up with minus the inverse cosine of x in terms of t over x max. And don't forget, this is also omega t minus t max. Great thing. Now we can multiply both sides by a minus 1. And now we can use the cosine on both sides. So that also means that x in terms of t over x max is just the cosine of minus omega t minus t max. But the cosine of minus x is just the cosine of x, so that's great. So we can get rid of this minus sign, and now we can multiply both sides by x max and see what we get. So this is equivalent to saying x in terms of t is equal to x max times the cosine omega t minus t max. And that's actually the solution to our differential equation. But that doesn't look too familiar. So maybe you might have seen a different form, but we can rewrite this. So what is our x max? It's the highest point of our pendulum. So that means that's the amplitude, the highest point, just A. It's not going to get any higher than x max because we are not going to put any more energy into the system. And now we get the cosine of omega times t. I'm going to leave it as it is. And omega times minus t max. Well, omega times the time is just seconds over seconds, so that's just a unit. But it's at the point t max. That means it's just some phase shift. I'm going to write it as minus phi 0, phi naught. And that's it. We've done that. That was a lot of work, but it's really fun. I like deriving stuff like this. I hope you enjoyed this too. We need a lot of stuff from this for further videos. If you did enjoy this video, please like and subscribe and recommend me if you like. If you want to support me a bit more, link to my Patreon will be in the description. And up until the next video, have a flammable day. See ya!
Also, um den Dreck, der hinten rauskommt, müssen sich die Polizei erst bei beiden Geräten keine Sorgen machen. Die Frage bleibt.